Today I want to talk about how we can secure the supply of critical minerals for the energy expansion, and also why we think we are the perfect marriage between oil and gas and renewables, or in other words, the marriage between old energy and new energy. We're kind of rethinking how we do the supply of critical minerals. Governments, companies are now looking for critical minerals all over the world in very remote areas. We hear talks about Ukraine, we hear talks about Greenland, and those places have one thing in common: they have very poor or no infrastructure. So it also means they will be very expensive. Even if we mine them in these remote areas, it's going to be very, very expensive for us to actually get them where we need them. We do things a little bit different. We rely on a different feedstock. We rely on wastewater from oil and gas. So it means that we can use things that we have right here underneath our feet. We don't go to remote areas, we just take what we have here, and in fact we take a feedstock that's already a big problem and that nobody wants. We do extraction and refining in the same facilities, also to minimize transportation and the environmental impact and the cost from transportation. And we do it very close to where we have the battery factories. So it means, again, less transportation, better for the environment, good for economy. We secure the local, the regional, domestic supply of critical minerals, which I think a little bit later in the presentation we're going to highlight why that is important. If we look to the lithium industry today, 90% of all lithium comes from very few countries. Comes from Australia, comes from China, comes from Chile, Argentina are the big producers. And they actually produce 90% of all the lithium in the world. And then again, we also have to say most of the top producer is in Australia. They produce more than 40% of the world's lithium. But they only break the ore and then they ship it to China. So it eventually means that China controls more than 70% of the lithium in the world today, which is obviously, and we hear about that in the news every day, that is becoming an issue, especially for the US, for Europe, and for other countries that would like to get battery manufacturing going as well. If we look to the lithium sources, about 2/3 of the world's lithium comes from hard rock mining, which is kind of the old technology. About 1/4 comes from solar evaporation ponds down in South America. We're going to get back to what these production methods are and also why we're different. And then about 10% comes from direct lithium extraction, which is basically what we do. We just do it in a little bit different way than anybody else. If we look to the US production, well, the US actually used to be a global leader in lithium production. Back in the 90s, 27% of all lithium was mined in the US. Today, it's less than 1%. And what we do know is that by 2035, 30% of the world's lithium demand will be right here in the US. So there's obviously a great gap between that less than 1% production and 30% demand. 87% of all lithium today goes to EV batteries. That has really been the accelerator for lithium demand. And then it's used in other industries like consumer electronics, various industrial applications as well. Again, EVs have been the huge accelerator for lithium demand. But we're seeing a shift there. EVs will continue to grow. In fact, by 2035, we expect that there will be more than 500 million EVs on the road globally. So that will continue to grow very strong from where we are today. But what we also see is that another segment is growing very fast, and that's battery storage. Battery storage to store intermittent energy resources like solar and wind is growing right now, and it's going to continue to grow. We also think that the grid will be a little bit more diversified in the future, or decentralized, if you will. Today, we're building big power cables and feeding homes and industrial companies with electricity. We think in the future, it's more likely that we're also going to see a decentralized grid where people have solar power in their homes in the factories and will supply maybe not 100% of the power they need, but a vast or maybe a big part of it. And that's also why we're going to see that energy storage is going to be more and more important for lithium. We are facing a lithium shortage. Up until now, the market has been balanced. In fact, there's been an overcapacity this year. Last year, we've seen lithium prices come down significantly, and that's because we have an oversupply. It is going to stay balanced throughout 2025, but already next year, we could actually be facing a lithium shortage. And the reason for that is that simply not enough lithium projects are planned. Down in the bottom here, we can see the projects that are already planned to come online. Some of them are more likely than others, but we can also see that that's not even enough. So lithium demand is growing fast, not enough capacity is planned. I actually read last week that it now takes an average of 18 years to bring new mining operations online. And if we apply that to this, we can see that we are not going to be able to handle that lithium shortage that we are facing now. And this is why we need to come up with new ideas, like ourselves, how we can set up operations much, much quicker. We use this, our planet is running low on power. Well, what we mean is that we are facing a lot of environmental challenges. And we think we have one of the keys to address that. But if we look deeper into what is the environmental challenge, well, we see emissions are continuing to go up very rapidly. We see that we reached a new high of 53 gigatons of CO2 equivalent in 2023. And despite agreements, this is not really going down. This is continuing to go up. And who is then driving the emissions? Well, it's the big players. It's China, it's the US, it's Russia, it's the EU. We all consume too much. We're driving that increase. In fact, what is interesting here is that we see China and India saw the biggest increase in 2023. The US actually saw a decline. But still too much power from oil and gas is used in the US, and we're going to try and see how we can think about it in a different way, not throwing out oil and gas, but do something different to take out, let's say, the biggest emitters of CO2, and then continue to do oil and gas in a more responsible way. 37% of all US emissions comes from transportation. So it means moving around is what is causing the most emissions that we see today. The second largest emitter comes from power generation, 31%. So if we could somehow address those two issues, we could actually lower CO2 emissions quite significantly. Electrification of transportation, addition of renewable energy is what we need to do that. And this is where we think that we have one of the keys to participate in that. I've been driving an EV for 4 years now, and this is the comment I get the most. EVs are not really more environmentally friendly because you have that battery production, and that initially causes a lot of CO2 emissions. And it's true, and it's the comment I get, and that's what we're fighting. But let's look into the numbers. It is true. When you produce an EV, there is a big emission, or there is a lot of emission from the battery manufacturing. In fact, it's an average 4.7 metric tons. If you compare that to a normal fossil fuel car, there is not that problem. A fossil car, you need 6.7 metric tons on average to produce it. That includes the whole vehicle. For an EV, it's 6.0 plus the 4.7 for the battery manufacturing. So it means initially, yes, we are behind. We use more emissions than you use to produce a fossil fuel car. But what we also see here, and that is very interesting, this is the use phase, the green one. So on average, in a fossil fuel car, in its lifetime, it emits about 49 metric tons of CO2. For an EV, that number is 8.2, so significantly lower. So it means that we make up for it. And the calculation today is that you have to drive 11,400 miles in an EV before it actually reaches that tipping point where it's actually more or greener than a fossil fuel car. We can actually change that quite significantly. We have a carbon neutral technology. We use a wastewater product. So it means that we can actually lower the emissions from the battery manufacturing from 4.7 to 2.5 metric tons. And it also means instead of having to drive 11,400 miles in the car before it becomes greener, we can lower that number to 3,700. We think that's a significant amount, and we think that will help consumers be more positive towards EVs and that transition, that they can actually see they're going to reach that tipping point much, much quicker. So what is it we do? Well, we take a wastewater product, we turn it into high-value minerals. And if we look at the different lithium technologies, well, we can do a rundown and see how they compare to each other. This is hard rock mining, and remember that hard rock mining accounts for about 2/3 of all lithium today. And how it works is that we break the ore, that's what you see in the top right here on the screen, in a huge area, which obviously causes disruptions to nature, to wildlife, and also pollution. Most of this is going on in Australia, and what we then do is we put it on a truck, because this is often in remote areas. We then put it on a ship and we sail it off to China, and then we process it. The process involves calcination, sulfuric acid roasting. Doesn't sound very nice, it is not. Leaching, which is basically using a lot of water. And then finally carbonization and refining. This is a production method with a lot of environmental footprint, and this is also why we get this pushback on the EV adoption. The other production method is brine solar evaporation. This is what predominantly is done in South America. It's about 1/4 of what we do today, lithium mining today. And here we do something different. We find deposits of lithium-rich water. We pump it to the surface. We then mix it with lime. And we then put it into evaporation ponds, which is what we see in the top right. Those evaporation ponds, we leave it for 2 to 3 years, maybe 4 years. The water evaporates, and we take out the lithium. This is not very sustainable either. It causes a lot of disruption to nature. It has a big environmental footprint in terms of pollution of soil and groundwater resources. And this often happens in areas with high water scarcity. And then we have the direct lithium extraction. This is a picture from China, in fact. And this is where most of direct lithium extraction takes place today. They do the same thing. They pump lithium-rich water to the surface, but then they extract it right away in a process that is very similar to what we do. The process doesn't take 3 or 4 years. It takes 2 hours. So you put it through the system, and you end up with lithium carbonate that you can now sell. This is a much more sustainable way of doing things. And when we compare things, we can also see that it is much more sustainable. The lithium yield, up to 95% we extract, instead of 20 to 40% by solar evaporation, for example. So it means we use more of the lithium that's actually in the water instead of letting it go to waste. The average footprint, 1.4 acres to produce 1,000 metric tons of lithium versus 115 for hard rock mining. There is very little pollution. Water consumption, just 80 million barrels per 1,000 metric tons of lithium versus 550 million gallons for solar evaporation. CO2 footprint, 1.5 million kilos to produce 1,000 metric tons of lithium carbonate versus, 15 million kilos, 10 times more for hard rock mining. So DLE is clearly a way of making lithium extraction, lithium production much more sustainable. So now it's so great, why don't we just do that? And we do. We do use DLE, but we do it with a different feedstock, and this is what we're going to talk about. We do many of the same things. The slide looks very similar to what we just saw for DLE. But what we do is we take a different feedstock. We take oil and gas wastewater. So it also means that we are not drilling to get water. We take a feedstock that's already on the ground. We co-locate with midstream operators. So it means they already have the pipe system to pump in the water. We just take it. This saves us a lot of years. It saves us a lot of money. Because what you would typically do when you want to do a DLE setup, you would go out, you would look for lithium-rich water. You spend some years doing that. You then find it. You acquire the land. You start filing for drilling permits. Maybe that takes 3 years, 4 years, 5 years. And then maybe you can get into production. Again, the average time to bring lithium operations online is 18 years. By bypassing all of that, we can do new lithium operations in just 18 months. We got our permits for the factories we're planning now in just 6 weeks. Because there's no drilling permits, there's no lengthy time to do that. We can do it very, very quickly. But other than that, we do the exact same things. We take the oil and gas wastewater, we do direct lithium extraction. In fact, we use many of the same technologies. And then we refine it, and then it's ready to go out to the customers. A factory looks like this. This is actually the drawing from our first factory in North Dakota. Produced water comes in. We put it to the pre-treatment separation concentration, which is kind of the secret sauce of what we do. Goes into direct lithium extraction. We do lithium concentration, and then finally refining and calcination, and we got the finished product, which is stored right here. So again, we do everything in one facility. So it also means that we minimize ground transportation. It's good for cost, it's good for the environment. If we then look to how are we different? Well, this is the same slide we saw before, but where we are different is that we only use 20 million gallons of water versus 80 for normal DLE. We're the same footprint. We're carbon neutral because we offset our feedstock against what we do. But the really big difference here is that we can set up a new 1,000 metric ton facility for $18 million. Normal DLE is about $45 million. Solar evaporation, about $50 million. Hard rock mining, about $60 million. So we are significantly cheaper. And it also means less invested capital. It allows us to do more projects. That's super important. But what is also important is we can do it in 18 months, not 18 years. And then finally, we actually also lower cost. We got this idea in 2012 when we did a pilot project with a big oil manufacturer. We discovered there was a lot of lithium in the water. We looked into it back then. There was no way for us to do it economically, so we left it. And before I invested all of my money into this, I wanted to make sure that we had a production method that was quicker, that was more sustainable, but also lower cost. Because what I learned over the years is You can be more sustainable than the rest, but if it's higher cost, nobody wants to pay for it. So I think it's important that we kind of cover all of that. It does have a compelling business case. I'm not going to go into it, but this is a facility that we're building right now. What I wanted to show you is that on the lithium prices that we are modeling, we have a payback period of 2.7 years. On the lithium prices that analysts following the industry are modeling, it pays back in 1.1 years. Super quick return. So how do we think the future of energy looks like? Well, what we can see here is the energy mix. And when we talk about the future, we like to talk about green energy addition. A lot of people use energy transition, but that means that something is going away and something new is coming in. And that's not going to happen. Oil and gas will be around for many, many, many decades. Let's be realistic. This is the predicted energy mix from now until 2050. And what we can see is oil is pretty stable. In fact, the production of oil will go up a little bit. Not because it will be a bigger part of the energy mix in the future, but because we use oil for many other things, like plastics, whatever. So in fact, oil will go down a little bit in the energy mix, and what will come is renewables. Total energy demand will grow by 80 exajoules between now and 2050. Renewables will grow 3 times, almost. Oil and gas will grow by 18%. And again, not because it's a bigger part of the energy mix, just because we need it for other things. This is also why we think that the future of energy will be diversified. We will need everything we can get. We need more energy. We need oil and gas. We need nuclear. We need renewables. And in order to store renewables, we need batteries. So how can we impact this in the most clever way? Now we know that oil and gas is going to stay around. It's not going away. Well, what we can do is we can target the areas where we have the highest emissions. And the highest emissions comes from transportation and energy generation. So if we can switch from fossil fuel into EVs, we can address that very easily. That will take away a lot of the emissions. So we think that's a good idea. If we can use more renewables instead of oil for energy generation, that also has a big impact, and that requires batteries. The future of energy is diversified. There is no single source that can cover everything. But we can do it in a smart, responsible way, and that's what we think is the way to do it. So by doing it smart, by addressing the biggest emitters, the industries that emit the most, we can help our planet back to 100%. That's all from me. Thank you.